Okay, so we're going to take a look at this ND Vanadate laser. It has a wavelength of 532. The mode of operation is continuous wave. The average power is 200 milliwatts or 0.2 watts. Again, we're using the ANSI default exposure duration for an unintentional or accidental exposure. We're using a 1 millimeter beam diameter at the beam waist. The divergence is 1 milliradian. We're using 1 over E squared and circular Gaussian. An observer range at a half a meter. Now, how do we get this description up there? If you type click that cell right there, you get a general information form up, and you can add in all sorts of stuff that if you want to hold on to and save that. Okay, so all I did was open this up and typed in ND Vanadate, and then I say save all, and it shows up right here. Right. So let's check our MPE. The MPE should be 2.55 milliwatts per square centimeter. The skin MPE is 3.11 watts per square centimeter. Our times skin MPE is 0.668. So it's under 1, so there's no skin hazard here. Our NOHD is 141.3 meters. We should not have a nominal skin hazard distance, and we don't. And that's obvious from this times skin MPE here. But not a bad idea to check. Make sure everything looks right in the software. Because at the end of the day, you're the LSO. Responsibility sort of falls on you to make sure that everything looks as it should be. All right. So let's talk about diffuse reflection for a moment. The diffuse reflectivity, spectral diffuse reflectivity. Spectral reflectivity, we set at 100%. What we're saying is for the diffusely reflecting material, and when we say diffusely reflecting, it's a Lambertian scattering, so it's a true scattering. Okay, that in the way the system models this, and also that's how the ANSI equation is based on Lambertian scattering. Okay. But we have a choice of how much power do we say is scattering off of this surface. If you want the worst case, put 100%. Now, in a lot of cases, it may not be, and if you're doing something more realistic, and you know you're dealing with a visible wavelength, and you're using something that's dark in color as an absorber, you wouldn't be scattering off this much power. But if you want the worst case, put 100%. Viewing angle, worst case viewing angle, is 0 degrees. A lot of times that's not very realistic because you literally would not be right in front of it based on system and machine configurations, probably off at the side, something like that. But worst case is a 0 degree viewing angle. Now, right now we're putting a beam on target, very small. That's because we want to analyze a point source. I'll just introduce this right now, but we're not going to get into this. My observer range I have set at 10 centimeters. I'm going to put something a little more realistic out here at 0.25. Okay, but then I'm going to say, well, my beam on target, we have a beam diameter of 1 millimeter. I can't imagine that. How would you get something smaller? Let's put 1 millimeter on it. What's going to happen is you notice this changes to an extended source. So this diffuse reflection section will automatically determine if it's an extended source and begin working the problem that way. And what that really means is that this system will use a MPE that's not as restrictive for the exposure duration that is used here. Now, the diffuse reflection has a separate exposure duration than the ANSI default. Let's put 600 over here. And you'll notice that for a 600 second exposure point source, dealing with point source, it's about 1 milliwatt per square centimeter. So you can see that the difference here is the fact that we're treating it as an extended source. In other words, it's making a little bigger image on your retina. Or I shouldn't say image. Well, that's it is imaging what your eye is imaging what it's seeing and making and so putting an image on your retina, but it's really about the spot size. So that it's a larger spot size than a point source. So you can take on a little more power, and so that's reflected in a little less restrictive MPE. That's enough for that right now. We'll talk a little bit more about this later, but that's why anytime we want to deal with just a point source, make sure the source type says point. Now this only applies to the retinal hazard region, 400 to 1400 nanometers. Outside the retinal hazard region, there's no meaning to point source or extended source because there's nothing being imaged onto your retina, right? So this only applies, point sources, extended sources are for the retinal hazard region, 400 to 1400 nanometers. But if you're in the retinal hazard region, let's just make sure we put a small beam on there, and we'll always be looking at a point source. Put this back to 1/4 second. Now you may ask, why don't we just use 1/4 second here? The reason we don't is a lot of times people are looking at a diffuse reflection for a reason, looking at the beam, what the beam profile sort of looks like. It used to be much more common than it is today, but it's often that diffuse reflections are something that we tend to look at for a reason. The other reason we might use 600 seconds is if we're dealing outside the visible, where we can't see the light and we have an accidental reflection, something like that. And so we typically use a longer exposure duration when we're analyzing diffuse reflection hazards. And so as a good place to start, we put 600 seconds. What you're going to find out is that a lot of times the MPE 600 seconds is as good as 30,000, which is an all-day exposure. Notice the MPE doesn't change. That tells you that the MPE, at least from 600 to 30,000 seconds, is the same. It doesn't vary. We could probably put this at 10 seconds, and we'll see that it's still the same MPE. So we could use 10 seconds or 30,000 seconds or 600 seconds. Kind of depends on what you want to do as the LSO. Sometimes when we're doing something for someone, we'll put 30,000 seconds in. We'll say, well, we're adjusting for an all-day exposure. That way, if the question comes up, we think we have something going on in a lab, it would be an all-day exposure. Why didn't you use 30,000 seconds? Go ahead and put it in there. You can say, we're analyzing it for 30,000 seconds, an all-day exposure. That's your worst case. But you know that it doesn't matter whether it was 10 seconds or 30,000 seconds. And you can go into the MPE table in the ANSI standard, take a look, and see where that occurs at in the line of the table for a visible, for 532 wavelength, for any visible wavelengths, okay? So I'll put this back to 600 because that's typically kind of just our default, our fallback position. You'll notice that the NHC here is about 8 centimeters, not very long at all. It's less than, about 3 inches or so. Okay, we report the skin diffuse reflection NHC, the MPE for the skin. Notice it's different than over here for the interbeam, and that's again based on exposure duration. See that the skin's MPEs now match up. Okay, and we also report the time skin MPE for a diffuse reflection, and you'll notice that we're not even close to 1. So there's no hazard from a diffuse reflection. If you don't have a hazard from an interbeam exposure, you definitely will not have one from a diffuse reflection. Okay, let's just pick up on a couple of other little things before we leave this particular example. We do report some correction factors here. Okay, here's C sub A. You can see that for 532 wavelength, we would calculate C sub B, which is the blue light correction factor. So you can find correction factors here. This is C sub A. Click that, you get C sub C. This is C sub B and C sub G. We'll talk about these at another time. Okay. Now, of course, this is labeled interbeam. If I want to know what the correction factors are for the diffuse, I can click here and I can get diffuse reflection hazards or correction factors. All right. Again, this is the average power irradiance that is being used, the average power irradiance of our laser that is being used to compare to the MPE. So we take, this was determined by the power passing through the limiting aperture, which is 200 milliwatts. We divide it by the area of the limiting aperture, and then we take the common log of it, and that's how we get, that's how we, let me start over. We take the power through the limiting aperture, divide it by the area of the limiting aperture. That gives us the irradiance of our laser. We then divide it by the MPE, and if the irradiance of the laser is larger than the MPE, when we take the common log of it, we will get an OD value. And so this divided by the MPE common log gives us an OD of 2.31. I think that's about it for this one. Okay.